All right, as I was saying, I don't know what 3 and 4 look like here. I think number 3 and 4 are kind of run-of-the-mill questions. In other words, they're not questions that are really challenging, but I know we sometimes get in the habit of just looking at those multiple choice numerical response questions. Make sure you were aware of what's expected from the textbook as well. If you look at the left-hand monitor here, there's a nice little summary of reflections. All of these things that I show you, like I've shown you a summary of horizontal and vertical translations. Now I'm showing you a summary of reflections. All of these things are going to be given to you at the end of the unit in a little package where you can see all of this to get ready for a unit exam. But we learned that there were 2 types of reflections yesterday. There's a third type of reflection that we're not going to talk about for a few days yet. One is a horizontal reflection, and you recognize the horizontal reflection as occurring because f of x changes to f of negative x. So, I had this conversation with a couple of you yesterday. There is some level of memorization here in this course. There really is. I mean, you need to, hopefully the memorization happens accidentally. You accidentally memorize it. Oh, f of negative x is a horizontal translation. I don't know that it's really memorization anyway, because I think this should make sense to you that if you change x to negative x, you're multiplying every x coordinate by -1. Everything should reflect horizontally. The crux or the difficult, sticky part of this is that a horizontal reflection is across the vertical axis. You need to wrap your head around that. That if the vertical axis or the y-axis is the line of symmetry along the center of my body, and I want to reflect something horizontally, I need to take this and move it over there, and this and move it over there. In other words, it's going to appear like that when I reflect it. So the horizontal reflection, the reflection this way, happens across a vertical axis. And the equation of the vertical axis, the equation of the y-axis is x equals 0. So now we're back to x equals 0. Oh, that makes sense. X is horizontal. But you can psych yourself out here. I've seen it many times. You can flip it again by mistake. Anyway, a vertical reflection is recognized as saying that y equals negative f of x. The reason why y equals negative x is a vertical reflection is because this is just, y equals negative f of x is just a variation, a different way of writing negative y equals f of x. And if you have negative y equals f of x, then you're multiplying the y coordinates by -1, which means they flip. Of course, that reflection is across the horizontal axis. The equation of the x-axis or horizontal axis is y equals 0. And the mapping here is really straightforward. For a horizontal reflection, x comma y turns into negative x comma y. For a vertical reflection, x comma y turns into x comma negative y, as expected. All that being said, can you take a look at the textbook problems for me, please, and the problems in your handout, and see if anybody has any questions you would like me to go over? Go ahead, Leslie.
Go over the third one on number 2.
The third one
On number 2.
in the handout.
Yes.
I understand. You want to talk about this?
Yeah.
Okay. So we understand, I'm not going to worry about the precise answers here, but we understand that the first part is a vertical reflection. And the reason it's a vertical reflection is because you have y equals negative f of x. So you're multiplying the original function, which is y, times -1. So what happens here is the mapping becomes this, which isn't really important to answering the question necessarily, but that's what's happening. When you look at the second one, since we're going from f of x to f of negative x, this of course is a horizontal reflection. And we know that the mapping as x comma y turns into negative x comma y, right? And I don't know exactly what we are after here. We're looking at invariant points. Okay. When you look at this, if I were to go from y equals f of x, and this is the one you're asking about, to y equals negative f of x, and I understand that that's not the third one. But if I went from that y equals f of x to y equals negative f of x, the mapping that would happen would be this, correct? Because it's reflected across the x-axis. It's reflected vertically. But if I go from any function to the identical function, so I'm looking at this now as being kind of the original function. I'm looking at changing this function. That's the original function. And I change that original function by changing the x to negative x, then that takes that function and reflects it horizontally. And the horizontal mapping is going to take this x coordinate in this ordered pair and multiply by -1. And it's going to take the y coordinate in this ordered pair and leave it alone. Right? And right now it's -y. And what I'm getting at, I could have very easily answered this question by saying, since there's a negative in front of the function and there's a negative in front of x, it is reflected both horizontally and vertically. So, and this is a good question that's being asked. If I reflect this horizontally, well, let's do the first one first, just to bring this all together. If I reflect it vertically, this point and this point will not move. That's why the first blank is 2. Should be anyway, right? The number of invariant points. No? Yours is different than this one. Interesting. Okay, let me pull that up. Just give me a sec. Just give me a second, please. And Leslie, can you give me a page number that this question is on? 11. This is the graph you're dealing with then, right? Okay. So I'll have to change that. I don't know why it's not matching my notebook file, but that doesn't matter. When we reflect this vertically, this will be invariant, this will be invariant, and this will be invariant because they're on the line of reflection. Every other point will move. That's why the first blank is 3. If we reflect this vertically, we get 3 invariant points because there will be 3 X-intercepts. If we reflect it horizontally, there will only be 1 invariant point, and you don't have any problems with that. So what if we reflect it horizontally and vertically? Well, let's start by saying, what if we reflect it vertically first? If we reflect it vertically first, then we will have these 3 points remaining the same. But then if we reflect the result, which will be this thing upside down, if we reflect that result horizontally, these 3 points, which were invariant, no longer are invariant, which means there would be 0 invariant points if we reflect it vertically then horizontally. I'm sure many of you have kind of figured out that the order of the reflections here wouldn't matter because if I reflect things horizontally, that point would survive the change. In other words, that point, if I reflected things horizontally, all of this would go over here, and all of this would go over here, but this point would stay the same, wouldn't it? Okay. So if I reflect it horizontally first, I get 1 invariant point. Now, if I reflect the result, which I'm not going to draw, vertically, that 1 point that survived that was invariant is all of a sudden going to go someplace else. And the question that I always ask when somebody asks about this question, which somebody always does, it's important that we go over it, is can you ever have an invariant point if you reflect the function both horizontally and vertically? Some of you are quick to say no, but there is a very special case where you could have an invariant point that survives both reflections. What would that point be, Arden? Right. If the graph, I'll just draw a graph here. If the graph happened to go through the origin, then when I reflect it vertically, the origin stays the same because it's an X-intercept. It's on the line of reflection. And then if I reflect it vertically, it stays the same as well. Anyway, Leslie, have I answered your question? Perfect. Take a look over your work and see if there are any additional problems. Go ahead.
For number 4, on that numerical response on page 12,
Is this match yours?
yes.
Okay.
For number 2, or the number 2, is
Yep.
wouldn't that be changing the x value and therefore being horizontal translation or horizontal?
No. Because if I take the original function f of x equals x squared plus 8, and I change it to f of negative x, that means I'm going to have negative x quantity squared plus 8. So there's a whole bunch of issues with us saying that this thing is a horizontal reflection. First of all, if it's a horizontal reflection, how could the 8 possibly change to negative 8? Right? It can't, because there's no x's in it. The other issue is what I keep going back to anytime we talk about substitution. When you substitute, you need to put in the thing you're substituting in brackets. When I square negative x in, I get x squared, because a negative squared is a positive. So what we end up with here is that f of negative x, a horizontal translation, gives you the exact same function. And this should, I hope, make sense to people, and then I'll wrap this up, because x squared plus 8 is a parabola that opens up with a y-intercept of 8, and it's centered on the y-axis. So if I flip that horizontally, it's still going to look the same. Okay. Since this has a negative 1 in front of the x squared and the 8 has been multiplied by negative 1, this would be a vertical reflection where we multiply the whole function by negative 1. We have to be very careful when we substitute negative numbers in to something that's going to raise those numbers to an exponent. Because if that exponent is even, that negative number becomes positive. Yeah. Are you talking now about this? Okay. Well, that's just, I don't quite know how you would arrive at that with either a vertical or a horizontal reflection. Well, you could arrive at it, but it would involve a combination of translations and reflections, which we're going to start talking about on Monday. Because negative x squared plus 8 looks like this. So if you took x squared plus 8 and reflected it vertically, it would end up being below the x-axis. Then you would have to shift it up to make it match that. So in terms of either a vertical, a horizontal, or both, you can never arrive at just that. You will either arrive at number 2, or you'll always be back at the first function. Yep.
Would there ever be a chance that you could have the negative x in the bracket over the 2?
You mean as part of the question?
Yeah.
I don't think so. I think if it's negative x in brackets and then it's raised to the 2, we would all just write x squared, including an exam. Okay, we're going to move on and start looking today at stretches. And once we complete this lesson, we will have learned about all of the pieces. We will have learned about horizontal translations, vertical translations, horizontal reflections, vertical reflections, and today we are learning about what are called horizontal stretches and vertical stretches. A stretch, just to give you a general idea of what we're doing here today, a stretch is taking a function and changing it in some way. And you need to, at the end of this lesson, understand how to recognize the properties of the stretch by looking at the new function, just like you have to understand the properties in terms of reflections by looking at the new function, or the properties in terms of translations by looking at the new function. Or, since we've been looking at an initial graph and a final graph, or an original and a transformed graph, and learning about how you decipher the translations from that, and how you decipher the reflections from that, well, now you have to decipher the stretches from that, whatever a stretch is. Now, the first thing after that I want to mention to you is the word stretch in the English language means, generally speaking, to make things bigger, right? But stretch in mathematics is not necessarily going to make something bigger. It can make things smaller. So if I have a coiled spring, maybe a spring from, I don't know, an automotive shock or strut or something, not a slinky, like it's pretty stiff, I can take these two ends of the spring and I can pull them away from each other, and that's considered a stretch, all right? But what I could do instead, and it's, I guess, what automotive strut springs are used for, is I could do this, right? I could squeeze it together, and that is considered a stretch as well. Okay, so I just want to get that out of the way, that a stretch doesn't mean making something bigger. So let's go through some terminology. This is all in your notes, so you can just follow along up here. If you decide to add something to your notes, you certainly can. Translations and reflections, which are those things that we've already talked about, are transformations. So transformation is a broad general term, and one type of transformation is a translation, which we spent 2 days on. One type of transformation is a reflection, which we spent 1 day on yesterday. They will change the orientation of the graph, so whether it's upside down or left, right, those orientations can change through a reflection. And they can also change the location, because if you translate the graph left or right or up or down, the position changes. But they don't change the shape. In other words, if I gave you a graph that's been transformed using everything we've learned so far, and you put a piece of tracing paper over it, and you trace the graph, you could pick that paper up and move it around somehow and put it on the new graph, and it would match. You might have to turn the paper over, because there's a reflection. You might have to rotate it, you might have to slide it, but the shape is exactly the same. A stretch is a transformation that will end up resulting in a change in the shape of the graph. And I don't mean shape like a V is a shape. I mean you can have a stretch and it will still be a V, but it will be a differently shaped V. It will be wider or taller or shorter or narrower. So, stretches make the graph larger or smaller. Graphs can be stretched horizontally or vertically, or both, just like they can be reflected horizontally or vertically, and both. So, what is a vertical stretch? A vertical stretch results in the new graph being taller or shorter. Okay, and I will show you a visual example of this in a second. There is something called the vertical stretch factor, and this is a very important idea. A vertical stretch factor tells you what happens to the graph vertically. And by looking at the vertical stretch factor, you can decide whether the graph is going to get bigger or smaller. You can think of the vertical stretch factor as a number, it is a number, that you multiply the height by to get the new height. So if the vertical stretch factor were 2, and I multiply the height of a graph by 2, the graph gets twice as tall. If the vertical stretch factor is 0.1, and I multiply the height of the graph by 0.1, it's going to get smaller. It's going to get shorter. And that's why I have this. I like number lines to explain things. It makes sense to me, and I think it makes sense to most students, that if this is a number line that represents different numbers that could be vertical stretch factors, a vertical stretch factor that's bigger than 1, like 1.5 or 2 or 100, is going to result in the graph getting taller. Sorry, I just wanted to check to make sure I hit record. I guess I did. And if you have a vertical stretch factor that's between 0 and 1, the graph will get shorter. I have an empty set at 0 and an empty set at 1 because if the vertical stretch factor is 1, then you're multiplying the height by 1 and you're not changing the height. You can think of 1 as being like 100%. And a number like 1.5 as being like 150%. And a number like 0.25 as being 25%. For that reason, we don't talk about negative vertical stretch factors. It doesn't make sense to say a vertical stretch factor is negative, and that will be important for later. So, for example, here's an original shape. This is not a function. This is not in your notes. This is an original shape. It's not a function. It's not a graph. It's just a shape. But if that function changes to that, you will notice that the new shape, the transformed shape, is just as wide as the original shape. If you measured it, they would be just as wide. But it's taller. And that means there's a vertical stretch. And when I indicate a vertical stretch like this that makes something taller, I draw arrows pointing away from each other. Because that's what happens. And I'm not going to measure it. If I put that ruler down and I measured the height of the object on the left and the height of the object on the right, I would discover that the new object is twice as high or twice as tall, so the vertical stretch factor is 2. Does that make sense to you? We're okay so far? All right. If I take this original one and I do that, the horizontal distance across this thing is still the same. It's just as wide, but it's been vertically stretched that way. So when I indicate or communicate to you a vertical stretch that makes something shorter, I draw 2 arrows close, pointing towards each other. And if I were to measure the 2 heights, you would discover that it's a vertical stretch by a factor of 1/3 because that second object is only 1/3 as tall as the first. Is this making sense to you? Okay. Horizontal stretches, well, I mean, I think if you get that, you get this. A horizontal stretch results in the new graph being wider or narrower. The horizontal stretch factor is going to be a number which tells us whether it gets wider or narrower and by what factor. And the same thing is true here. On a number line, if you look at numbers that are horizontal stretch factors, we don't have negative horizontal stretch factors. By the way, if the parameter that's going to tell us the stretch factor is negative, then there's a reflection as well. Okay, that's where we're going with this. But if the stretch factor is between 0 or 1, it's what we could call a compressive stretch. Squeezes things together. But if the stretch factor is greater than 1, then it's a expansive stretch. So this would be a horizontal stretch that's expansive, and it's by a factor of 3 because the thing is 3 times as wide. This would be a horizontal stretch that, by the way, I'm using expansive and compressive. Those aren't math words. Those are just words that might help you understand what's going on. And that's a horizontal stretch. Again, notice I'm putting the arrows pointing towards each other to indicate things are squeezing together by a factor apparently of 1/4. So if I measured the widths, I would find that the one on the right is only 1/4 as wide. So essentially, whether you're talking horizontally or vertically, this line that you're looking at on the screen right now is indicating whether something shrinks or grows, right? The stretch factor is more than 1. Think of 1 like 100%. So if the stretch factor is 2, the new object will be 200% the size. vertically or horizontally, depending on what we're talking about. All right. So now we are going to stretch these functions. And I don't want to spend really too much time on this. But we're going to take all of these points and stretch them. Oops, sorry. Thank you. Did I give you one? No. And stretch them. But there's a little issue we have to deal with here. And it's that we are always going to be stretching things relative to the axes. Oh, thank you, Leslie. So, when this says, does everybody have a ruler? When this says we want to stretch this graph vertically by a factor of 2, what that means in this course is every point is going to move twice as far away from the x-axis. We're not just going to arbitrarily draw this thing twice as tall. It has to be stretched in a certain way. So, for example, starting on the left, well, you know what? I'm going to do this point first. This particular point on the original function is 2 units away from the x-axis, and that's a measurement of vertical height. If I stretch this vertically by a factor of 2, it is going to be 4 units away. So everything is being stretched relative to an axis. If I take a look at the first point, the one that I skipped over because I wanted to deal with this one first, this point is exactly 0 away from the x-axis. So its height is 0 relative to the x-axis. If I stretch a height of 0 by a factor of 2, it's still 0. Which means this point is going to be invariant. And when we connect these points, we will get a piece of the transformed graph. And I move on to the next point, which is this one. This point is 4 units away from the x-axis. So if I stretch it vertically by a factor of 2, it will be 8 units away. And then we can connect the points and add another piece to the transform graph. The fourth point from left to right is 4 units away. Double that because the stretch factor vertically is 2 and it has to be 8 units away. Then we can connect the points. And the last point that I have labeled with a dot on this graph is 4 units below the x-axis. So if I stretch it away from the x-axis vertically, it's going to be 8 units below. And if you do a very tidy job of this, a very accurate job of this, you will discover that when you connect these 2 points, they will go through the x-axis at that x-intercept, which, I mean, that makes sense because that x-intercept is not above the x-axis, so it can't get further above, and it's not below, so it can't get further below. It's an invariant point. So we're learning here, by the way, just like vertical reflections, that the x-intercepts are invariant when you vertically stretch. Circle the invariant points. I'll circle them in green. It doesn't matter as long as you understand that they're invariant. I think that's pretty straightforward. Any questions with A? Okay, let's vertically stretch the same graph by a factor of 1/4. Well, I think we've already established that since this point at -6 for x and this point at +5 for x are neither above nor below the x-axis, you can't stretch them relative to the x-axis. This point is 2 away from the x-axis. If we want to stretch it vertically by a factor of 1/4, we have to figure out what 1/4 of that distance 2 is. So 1/4 of 2 is 1/2. This point is going to end up being here. I suppose in keeping with the pattern that I've established, we should connect that. The next point left to right is 4 away, and if I stretch that vertically by a factor of 1/4, it's going to be 1 away because 1/4 of 4 gives you 1. And this whole first set of examples is merely to get you used to what a stretch factor means. This point, which is 4 away, will also be 1 away. This point where x is 6 is 4 away. This point is 4 away, but it's 4 below. So 1/4 of 4 away is 1 away, and it will be below. And again, if you've done a fairly decent job of this, you will discover that everything lines up well. Circle the invariant points. No worries. X-intercepts. X-intercepts are invariant points when it comes to a vertical stretch. And again, I don't think that's a memorization thing. I don't think you should go, oh, I better memorize that. X-intercepts are invariant with a vertical stretch. I think it should make sense to you. Any questions with B? I think you're getting the hang of this. Horizontally stretch this function by a factor of 3/2. So if we're going to stretch things horizontally, we're going to have to do so relative to the y-axis. Is it clear here that 3/2 is 1.5? Okay, I mean, sometimes it's useful to think of decimals. So anything that is to the left of the x-axis, anything that is to the left of the y-axis will end up being 1.5 times further to the left. Anything to the right of the y-axis is going to have its distance to the y-axis multiplied by 1.5, so it'll be 1.5 times further away. Which means anything on the x-axis will be invariant. We could even put that right there. We could even circle it right now that has to be invariant. Starting with the left-hand point, 1.5 of 6. This is 6 away from the y-axis. 1.5 of that is 9, because half of 6 is 3. 6 plus 3 is 9. This point is 4 away. It's 4 to the left of the y-axis. 1.5 times that distance of 4 takes you to 6. And now we're starting to get a shape of the graph. But we're not done, of course. We have those other 2 points to tackle. This is 4 away. 1.5 of 4 is 6. The final point on the bottom here is 6 away. 1.5 of 6 is 9. And if we connect those final 2 points, we complete the picture of the transformed function. Questions with C? All right, and horizontally stretched by a factor of 1/2. Well, this is 6 away, so half of 6 is 3. It will be 3 away. This point is 4 away. Half of 4 is 2. We can connect them. This point is 0 away. Half of 0 is still 0, so it's still 0 away. In other words, it's invariant. And again, at some point, we're asked to circle the invariant points. This is 4 away. Half of 4 is 2. And this point is 6 away. Half of 6 is 3. And we complete the picture of the transformed graph. So all we've done so far is talked about what the stretch factors mean and what they do to the graph. Does anybody have any questions here with any of this so far? All right. So this says exploration, and it asks people to use your graphing calculator. I'm not going to do that. I have the graphs loaded. If you want to explore with your graphing calculator later, this would be the set of instructions you need to follow. We are going to be looking, everybody, at graphing y equals sine of x. So let me show you the graph of y equals sine of x. That's the graph of y equals sine of x. And it continues in both directions. And again, if you want to do it on your graphing calculator later, that's fine, but please focus up here. If you can focus and do it at the same time, that's fine, but I don't want you to lose sight of what I'm saying. So we're going to be looking at stretching this graph, all right? And when we take a look at the first part of this exploration, it says sketch the function, so I've already done that. And then it says write the equation of all of these functions and find out how the original graph changes. So what's happening here with y equals 2f of x, if f of x is sine of x, then that means y equals 2f of x is y equals 2 sine of x. It just means 2 multiplied by sine of x. And I'm using sine of x because it doesn't matter what the function is, and sine of x is kind of a cool graph to look at. I suppose the equation of y equals 3f of x would be y equals 3 sine of x. Y equals 1/2 sine of x would be 1/2 f of x. And the last one, 1/3 f of x would be 1/3 sine of x. So the question is, everybody, how does this graph compare to the original graph? And how does this second graph compare to the original, et cetera, et cetera? Well, let me show you. And again, you could do this on your graphing calculator. I'm going to graph now y equals, what was the first one? 2 sine of x? Okay, so there's sine of x. It wobbles up and down vertically. It peaks at 1. It valleys at -1. By the way, again, it continues in both directions. And if I graph y equals 2 sine of x, this is what it looks like. So look at the invariant points. The invariant points here are x-intercepts. None of the x-intercepts on the original function changed. But if you look at the peak of the new function, which is in blue, it peaks at 2. And if you were to take any point, say this one, and look at the y-coordinate and double that y-coordinate, then you're going to get the new y-coordinate. So this is a vertical stretch by a factor of 2. I just want to make sure everybody sees that it's a vertical stretch. And since it's twice as tall, it's by a factor of 2. Is that ringing true to you? Okay, so let's write that down. But, you know, we're going to have a lot of writing to do here. Why don't we be smart about it and abbreviate? This is a vertical stretch by a factor of 2. Don't do this on a diploma exam. Don't do this on a written response question. So we are creatures of learning from patterns that we've seen previously. Do you think there's a connection here between the fact that it's vertically stretched by a factor of 2 and there's a 2 that we've multiplied the function by? No, we would hypothesize that this function is stretched vertically by a factor of 3. We're hypothesizing that the number in front that you're multiplying the function by is the vertical stretch factor. If that's the case, then this should be a vertical stretch by a factor of 1/2, which, since 1/2 is less than 1, that could be a description of what's going on. And this would be a vertical stretch by a factor of 1/3. So now I'm going to show all of these to you. But again, we develop more abstract rules so that we don't have to waste time all the time looking at concrete work like graphs or tables of values. So I'll turn off 2 sine x. Here's 3 sine x. I'll give you a second to mentally digest the fact that that is a vertical stretch by a factor of 3 in going from the pink graph to the new graph. This is 0.5 sine x. I'll give you a second to mentally digest that the pink graph has been squished by a factor of a half. By the way, I know it's tempting to say squished by a factor of 2, but that's not a good idea. It's been stretched vertically by a factor of a half because every point is half as tall. And this is a third, and you can see it's a third. All right. So, write a conclusion. When we go from y equals f of x, when we go from y equals f of x to y equals a times f of x, okay, now we have a new parameter. You had h, you had got k, now you got a. There's a vertical stretch by a factor of a. Now, I'm going to add absolute value of a. That's not important in any of the illustrations I just showed you. But if a is negative, if you look up here on the left-hand screen, if a is negative, then you're really multiplying the function by a negative, and it reflects vertically. Well, if a is negative 5, then the function will reflect vertically, and it will be stretched vertically by a factor of 5. We would never say it's stretched vertically by a factor of negative 5. There might be a negative as part of the a, but you don't include it when you talk about the stretch factor. All right, let's take a look now at these. So this time we are multiplying x by something. Remember that f of x is sine x. So if I said, what is f of 2x? It's sine of 2x. So this time we're changing the input of the function. We're not taking the whole function and multiplying it by 2. We're multiplying it by 3. We're multiplying the x that we're using in the function by 2 or by 3 or 1/2 or 1/3 or whatever number we want. I hope it's clear. I'm using sine of x, but we could have picked any function and we would be learning the exact same outcomes. So I know this, I'll tell you right now, things have been going along very smoothly, almost flawless for most of you. This is going to be where the hiccup happens. Okay? Because when you take a look at y equals sine of 2x, when you take a look at y equals sine of 2x, you would expect things to stretch horizontally by a factor of 2. Okay? And everything we've learned so far in this unit really can be connected really to parabolas in Math 20. Except we never really horizontally reflected them. But that's not a big deal. There's nothing in Math 20 to compare to this. Let me show you what the graph of y equals sine of 2x looks like. It's not stretched horizontally by a factor of 2. It's stretched horizontally by a factor of a half. If I just look at this side of the graph, and highlight the original graph, I guess I'll highlight it in magenta. Here is the original graph. It goes through one complete cycle, and for those of you that have taken Physics 20, that's like one wavelength. But how many of you have taken Physics 20? Few. It's like a wavelength. That's how long it takes to repeat. But when I take a look at the blue one repeats in half the distance. It's hard to imagine or visualize, but you take that pink one and you stand over here with your hand against this and you push it that way until this point gets here. And we will have squished the thing and it is half as wide, which means the horizontal stretch factor here is 1/2. This has been stretched horizontally by a factor of 1/2. Just wait until I get through all four. Okay. Again, being creatures of learning from experience, we would suspect then that this will be stretched by a factor of 1/3. And if it is stretched by a factor of 1/3, then this point, which by the way is over at 360, should go over to 120, shouldn't it? Because the third of 360 is 120. And 120 is, each of these is, I think, 90, 30, another 30. I think 120 is there. So this thing should go up, down, down, up. It should look like that. Take a look. Yep. If you had to guess what's going to happen here with 1/2 x, I think it's reasonable to say you think it's going to stretch horizontally by a factor of 2. So what's happening is the opposite. The number you're putting in front of x is not the stretch factor. The reciprocal of that number is the stretch factor. And this will be stretched horizontally by a factor of 3. And just to show that to you, I might have to change the window settings here. Here is 0.5x. I don't need to. If you're watching this on video, you're missing out on a little bit. This red graph starts here at the origin. It's going to go up to this point that I'm indicating here. Then it's going to go down and it's going to continue. But that complete up, down, down, up will be twice as long. And if I were to do, another way to look at it is, the distance from here to the peak of the original one is 90. The distance from here to the peak of the new one is 180. It's twice as far. And if I were to show you the one that had 1/3 of x, that peak is 3 times further away. It's over at 270. So the conclusion we draw is that when we go from y equals f of x to y equals f of bx, b is another parameter. So we've got a, we have b, we have h, we have k. That there's a horizontal stretch by a factor of the reciprocal of b, and I'm going to put the absolute value of b there, the reciprocal of the absolute value of b, for the same reason that I did with the absolute value of a. That reason being we don't want to have negative stretch factors. So let me run through the summary and then see if there are any questions. The summary is on the next page. And again, The hope is that by going through this almost excruciatingly slow, you really understand it, and then the examples are just rapid fire. So with a vertical stretch, what happens is you take the y coordinate of every point and you multiply it by some number. That number is called the vertical stretch factor. This summary point has to do with the graphs we did on the first page of this lesson. We use a parameter called A for vertical stretches and or reflections. So I'm connecting what we learned yesterday, which is on the left-hand screen here for you, where if you have a negative in front of the function, there's a vertical reflection. I'm marrying that with the concept of A being a stretch factor, because if A is negative 12, then you have a negative in front and it's reflected vertically. But the A including a 12 means it's stretched vertically as well by a factor of 12. The equation of the function goes from y equals f of x to y equals a f of x, a times f of x. The vertical stretch factor is a. Okay? Absolute value of a. And then I'm telling you here, if a is negative, there's also a vertical reflection. I could tell you that this is the mapping, and I want you to think carefully about this. The mapping, when you introduce a, is that y becomes a times y. Not the absolute value of a times y. A times y. Because think about it for a second. If a is negative 3, then each y coordinate gets multiplied by a negative to reflect it across the axis, the x-axis, and each y coordinate gets tripled. So each y coordinate gets multiplied by negative and by 3. And invariant points are on the x-intercepts. They're points on the x-axis because they're not affected by a vertical change relative to the x-axis. Horizontal stretches, the x-coordinate is multiplied by the stretch factor, moving it closer or further away from the y-axis, but the y-coordinate does not change. We use the parameter b, but unfortunately, when we go from y equals f of x to y equals f of bx, the horizontal stretch factor, and I have a typo there. Do you have the word vertical or horizontal? You have horizontal? Same thing that happened yesterday. I copied and pasted, but I missed changing one thing. So this should say horizontal up here. And it does say horizontal in your note package. So the horizontal stretch factor is not b. It's the reciprocal of b. Or more specifically, the reciprocal of the absolute value of b. If b is negative, there's a horizontal reflection. And the mapping is this. And can you tell me, do you have absolute value signs in the mapping? Good. Again, something I copied and pasted but forgot to edit. They shouldn't be there. It should be what you have in your notes, because if b is negative, that negative has to get multiplied by x to get a new x coordinate. And invariant points are y-intercepts. So that, in a nutshell, is a summary. I don't want to spend too much time getting into a whole bunch of depth with it, because we have some examples to go through, but you did have a question, Ian. Correct. B is the parameter that you multiply x by, but b is not the stretch factor. The stretch factor is the reciprocal of b. And by the way, reciprocals are unidirectional. That's maybe the wrong way to put it. If the stretch factor is the reciprocal of b, then b is the reciprocal of the stretch factor. They're reciprocals of each other. Okay. All right. Write the equation of y equals f of x if I vertically stretch it by a factor of 5. Well, That's it. This is all there is to this example. If I vertically stretch a function by a factor of 5, you need to know that a vertical stretch means you multiply the function by the stretch factor. And by the way, if there were a reflection, then we would put -5, if there were a vertical reflection. Horizontal stretch by, I'll be clear here, and I don't know that you need to write this, A equals 5. Can you tell me what B is equal to? Think about what B is equal to in the second question here on the screen. Madison, do you know? It's 4. It's the reciprocal of a quarter. So since B is 4, it's y equals f of 4x. Vertical stretch by a factor of a quarter, and a horizontal stretch by a factor of 5. This would be a multiple choice question where you have a number here and here. And maybe in choice A, the number in front of this is 4, and in choice B it's 5. And then, so it might be 4, 5, 4, 1/5, 1/5, etc. What are the numbers? Well, the vertical stretch factor is a quarter, so that's A. The horizontal stretch factor is 5, which means B is a 5th. This will be where you stumble. So the number that goes in the equation is not the stretch factor. The number that goes in the equation is the reciprocal of the stretch factor, which we call B. D, a reflection across the x-axis. Well, that means that it's reflected vertically, so it has to be negative something. Vertical stretch by a factor of 2. Horizontal stretch by a factor of 1/3 means that B is 3. And I realize I'm going through these pretty quick, but it's just a few things you have to remember. A is the vertical stretch factor, basically. B is not the vertical stretch factor. B, the number you put in the equation, is the reciprocal of the vertical stretch factor. Any questions with A, B, C, or D there? All right. What happens to the graph of a function f of x if I replace x with 3x? Well, that means we're creating this. So what happens? That. And what's going to happen, and I just saw a couple people go to put their hands up. So, and I understand this is what's going to happen. You're going to second guess yourself. You're going to flip something over, and then you're going to go, yeah, but I got to flip it over again. It can be tricky. If we put 3 in front of x, this is saying b is 3. That's what it's saying. Okay. Now things get goofy. If I take y equals f of x, and I replace y with 3/5 y, what is the value of A? What is the value of A? Keep in mind, this is our template today. Y equals A f of bx. This is our template. And in question A, we were just using y equals f of bx because there was no A. Well, there was, but A was 1. Over here, we're using y equals A f of x. Who can tell me the value of A? Shizmaida. It's 5/3. Because when we rearrange this equation for y, we have to multiply both sides by 5 and divide both sides by 3. So that means we have a vertical stretch by a factor of 5/3. This is meant to illustrate to you, and this is very tricky and I don't want to spend a lot of time talking about it. That you know how we have to flip B over, but we don't have to flip A over to get a stretch factor? The reason for that is A has already been flipped over because it's no longer with the Y. When you have a number in front of X, you have to flip it to get the stretch factor. When you have a number in front of Y, you have to flip it to get the stretch factor. But we don't write it as AY equals f of bx. Somebody has decided to put the A on the other side already and just call it A, not 1 over A. That's really tricky. But I'm just giving you this to explain to you that there's no discrepancy here. We treat X and Y the same. It's just that somebody's already flipped the A. Replace X with 1/6 X, Y with 5/2 Y. Do you have this question? You do, okay. This becomes Y equals, well, it becomes 5/2 Y equals f of 1/6 X, which we rearrange for Y and get 2/5 f of 1/6 X. So A is 2/5, B is 1/6, which means the vertical stretch factor is 2/5, and the horizontal stretch factor is 6. Because the horizontal stretch factor is the reciprocal of B. The vertical stretch factor is just A. Okay, write the equation of the image of y equals x squared after a horizontal stretch by a factor of 3. So B is the third, which means the function is y equals f of a third x. But since we know f of x, we can put a third x into the function. If f of x is x squared, then f of a third x is 1/3 x squared, or 1/9 multiplied by x squared. Absolute value of x. If I have a vertical stretch by a factor of 1/4, that means A is 1/4. If I have a horizontal stretch by a factor of 2, that means B is 1/2. There's a horizontal reflection across the y-axis, so if it's reflected horizontally, B actually is negative as well as being 1/2. I want to ask you a question here. Without me resorting to this, how many of you see that the equation of the function will be this? Basically, you put the A in front of the whole thing, and then you change the x to bx, or you put the b in front of x. You could certainly use the function notation, but you don't have to. That says negative 1/2 x. A little too much coffee for me this morning, maybe. And that's it, right? So I really am never happy when I only leave you with like less than 15 minutes to work on stuff. But this lesson includes that wrinkle of the reciprocal of B. And every one of you are going to, as I say, stumble from time to time. So I felt if I went a little slower, it would be better. You've got some practice problems here, a whole slew of them from the textbook, and then some multiple choice numerical response questions. You need to, if there's anything over the first 4 days of this course that you're unsure of, you need to get it clarified for Monday, because what we are going to be doing Monday is putting the whole shebang together and graphing y equals a f of bracket b bracket x minus h n bracket plus k. We're going to have to put it all together and do it all at the same time. Well, not at the same time, but in steps for a single question. So I'll zip my app and let you guys get to work. And I'll come around and I'll give you a hand. Of course.